Question 19. Storage cells and fuse cells are types of electrochemical cells. The electrodes potentials for 5 redox systems are shown in the table 19.1. A student sets up an electrochemical cells based on redox system 1 and 4 in table 19.1. Draw a label diagram to show the cells could be set up in the laboratory. So we're looking at redox system 1 and 4, which is 1 and 4. And the diagram expected to be drawn is shown below here. And we're looking at chromium 3 plus redox, and we're also looking at manganese redox, manganese 7 plus redox. And the table has a chromium electrode. We have the chromium 3 plus aqueous solution, a platinum electrode here, and 1 mole per decimeter cube solution of either potassium permanganate or manganate solution. We have the salt bridge as well, and a voltmeter to measure the potential difference between the two electrodes. So that's a voltmeter, and it measures the potential difference between the two electrodes. Part 2, we need to construct the equation for the overall cell reaction. It's got 4 oxygen, so it's going to form 4 water. That's liquid. And the manganese 7 here will form manganese 2 plus aqueous. In order to balance the equation, we have 8 hydrogen here, so we have 8 plus here from the acid, and the plus 2 charge here, and the overall charge on the left is plus 8 minus 1. So that's plus 8, and that's minus 1, which makes it plus 7. And we go plus 2, so we need 5 electrons here, and that's why we had 5 electrons there. Also, we have chromium solid being formed, so that has to be reversed. Why? Because the more positive stays and the less positive will be reversed. So this has to go that way because it's less positive here. So that's why chromium is in this direction. That means chromium is being oxidized, and the potassium permanganate or the manganate will be reduced. The reduced is gaining electron, and the oxidized is losing electron. So we have to times that by, because we got 3 electrons being given off, and he needs 5. So we have to times that by 3 and times that by 5. So we get, if we times that by 3, we get that. And if we times it by 5, we get this. And then we draw a line in there. And then we find the overall equation. So this one is reduction here, and this is oxidation here. Reduction equation, oxidation equation, and overall equation is here by 15 electrons cancel 15, so that goes. And then we write the rest down here. So that's 12 water. So it's 12. 3 manganese 2 plus, 3 manganese 2 plus, 5 chromium 3 plus, 5 chromium 3 plus. 24 H plus, that's H plus aqueous. 3 manganate ions, that's 3 manganate ion. 5 chromium, 5 chromium. And now, so we can write that here. Finally, this is the final answer here. B. In acid conditions, manganate aqueous solution disproportionate to form manganese dioxide and manganate -1 ion. I. Explain in terms of oxidation numbers why disproportionation has taken place. So for disproportionation, you would have oxidation and reduction taking place by the same species or by the same ion. We got manganese 6 plus here because the overall charge is -2. Oxygen is 2 minus. 2 minus times 4 is 8 minus. And if you have overall charge of -2, you must have plus 6 here. And the oxidation number for this one, manganese here, will be +4. If this one is -2, -2 times 2 is -4, and overall charge is 0, so manganese must be +4. And the oxidation number here will be +7. If this is -1 overall charge, and this is 2 minus times 4 is 8 minus, and to get overall charge, this must be +7. And we can see from these two that oxidation has taken place. So the +6 going to +7 is oxidation, and +6 going to +4 is reduction. And so to explain that, Mn is being oxidized from +6 in MnO42- to +7 in MnO4-, and Mn is reduced from plus 6 in MnO4 minus to plus 4 in MnO2. Explain in terms of electrode potentials the equilibrium shift why MnO4 minus occurs disproportionate in acid condition. Use the information in table 19.1. The redox potential for the redox system shows that going from MnO4 minus to MnO4 minus is 0.56 volts. It's less positive. If we look at the redox table, so you're going from MnO4 minus to MnO4 minus is 0.56. That's positive. And if you're going from MnO4 minus to MnO2, this is plus 1.7. So this one is more positive and this is less positive. So plus 0.56 volt is less positive, and less positive, that means shift left. So that means it's going to be going that way, reverse. So that is an oxidation because we're going from the MnO4 minus to MnO4 minus. So that's a shift to the left. And the fourth one is going from, for the reduction, which is the one that stays because it's more positive, and so that's a reduction, more positive, stays. And C, an alkaline hydrogen-oxygen fuel cell is set up. The overall equation for the cell reaction is shown below. 2 hydrogen gases plus 1 oxygen gas giving 2 water liquid. Redox system 2 in table 19.1 is the positive electrode of the cell. 1. Write the half equation at the negative electrode. Part 2. The cell potential is 1.23 volts. Calculate the electrode potential of the negative electrode. Part 3. State one important features of a fuel cell that is different from a conventional storage cell. For part 1, the hydrogen gas is going to give 2H plus 2 electrons. So we add 2OH minus to remove H plus ion. 2H plus, 2H plus, that's the hydrogen gas, plus 2OH minus to give you 2H2O plus 2 electrons. So 2H plus 2OH minus will form the water, because that's the 2H pluses which goes there, and then the 2OH minus which will then form the water. For part 2, the electrode of the right is the most positive, and to calculate the electrode of the negative, we need to write the equation. The E cell is equal to E right minus E left. The E cell is 1.23 volts and the E right is 0.4, which will be the most positive, and we got that from the table 19 here, which is 0.4. And therefore, we find EL, electrode of the left, which is 0.4 minus 1.23, and that equals minus 0.83 volts. For part 3, we need to state one important feature of a fuel cell that is different from a conventional storage cell. And in a fuel cell, you do not recharge, but you add more fuel, such as hydrogen gas, to it. Fuel, the hydrogen gas, reacts with oxygen or oxidant to give electrical energy or voltage. This is the flow of electrons we're talking about here. It's the flow of electrons that gives electrical energy or the voltage, because the voltage is supplying the energy to the electrons.